All right, so we are live. Oh, okay, welcome everyone. Welcome to this wonderful session on AI for AI in Earth Sciences or AI for Earth Sciences. It's the same thing. And today is going to be one of the very, very important sessions. And it's by Dr. M.L. Virdi. And Dr. M.L. Virdi works as a senior research scientist at NASA Langley Research Center, and he has a wonderful experience in processing the big data, as well as the deep learning, machine learning, as well as building the hardware infrastructure, IoT devices. And I would let Dr. Amal Virdi introduce himself. Please go ahead.
Hey, good evening, everyone. This is Makhan Virdi. I thank you for the introduction, Sandeep. So, as Sandeep told you earlier, artificial intelligence and earth sciences both are very important fields. Earth science because we live on the planet, and artificial intelligence because for the past decade or so, it's one of the most important topics. Most important tool for any science or any engineering problem. So when you combine both the very state-of-the-art technology and the planet that we live on, you can solve some really important global problems. So the session today is barely an introduction to earth sciences, artificial intelligence, and how they can help each other, using AI as a tool to understand the processes that happen on the planet. So feel free to ask any questions. I would try to answer them to the best of my capabilities. And it's a webinar. It's not one way. It's interactive. You can stop anytime if you have any questions, if you want to learn more about it, if you want to go deep into the weeds of certain technological aspects that I'm going to discuss. Please go ahead and ask questions. It's more of a discussion. It's a learning opportunity for me too, because you all are from different domains of science and engineering, so you have different perspective. And when we are trying to solve problems that are at the scale of earth sciences, at a planetary scale, we need people from all kind of backgrounds. And everyone who comes from a different background, they bring a different perspective. And when you're trying to solve human problems at such a scale, we need all the opinions, all the perspective to make an informed decision, the decision that is going to affect everyone who lives here, who drinks, eats, and breathes all the resources that we have on the planet Earth. So for those of you who are not very familiar with the planetary sciences and how they are divided into different subsystems, this is just an overview of what it is. So Earth is made up of 5 major parts, or you can call them subsystems, according to the processes. The first one is atmosphere, which is just a thin layer made up of a mixture of gases and particles suspended in the air that surrounds Earth. Predominantly nitrogen, then comes the oxygen, very vital. Trace gases like argon, carbon dioxide, H2O, which is moisture. The next one is hydrosphere. We commonly call it like water cycle. It's the sphere that includes the liquid ocean, the inland water bodies like lakes and streams and rivers, wetlands, uh, and groundwater also. So that's the water portion of planet Earth. Then we have ice, which is also called cryosphere, cryo for frozen and sphere for planet Earth. So it's a subset of hydrosphere where the water is frozen. So you can either combine it with water or you can study it separately as cryosphere or ice. The reason we do that is with the global warming and climate change, we need to separate the water that is available to us through oceans and through freshwater lakes and rivers, and the water that is frozen on the ice on the polar regions. The next one is land. You can call it geosphere to be technical. That's the sphere that includes solid earth, the core, the mantle, the crust, and the soil layers where we do agriculture and all the things. The next one is biosphere, that consists of all of Earth's organisms, including humans, and the matter that has not yet decomposed. So that is part of the biosphere. So basically, biosphere sort of exploit all the other spheres to sustain life. So that's just a basic introduction. Some of you might be very familiar with some or all of these different units. It's great. So before we dive into earth sciences and get into the weed of different problems that we have on planet Earth, let's just get a perspective of different perspective from different point of views. There are 100 billion different galaxies in the universe. There are more than 250 billion stars in the Milky Way galaxy alone. Sun is just one of those 250 billion stars, and with only Earth as one of the orbiting planet that supports life. So just to give you a perspective that it's a small mote of dust suspended in the vastness of nothingness. And it's supporting life for approximately 9 million different species of flora and fauna, or plants and animals. However, humans are in the driving seat. We are driving most of the global change with our intelligence. So if you look at the first image here on the top left corner, that's an image taken from Cassini spacecraft. You can see through the brilliance of Saturn's ring. You see on the top half of the picture that arrow points to planet Earth in that red circle. Second picture on the right is taken from Mars, not from Mars, but from Mercury, and that those two things that are bright in that red circle is planet Earth and Moon, reflecting sun's light, and this is from 98 million kilometers from another probe called Messenger. And if you look at the bottom left image, the one that is moving, that is actually an image that is taken daily. More than daily, it's taken multiple times daily, I think 10 times in a day. And that is taken from a stationary point 1 million miles away from planet Earth. So if you look at the second image from at the bottom, the one with the sun in the center and L1, L2, L3, L4, and L5, those are called Lagrange points. So those are the points where the gravity of sun and planet Earth cancel each other, and all the other forces due to the movement of Earth around sun, they get cancelled out. So if you place any object in any of those at any of those 5 points, it's not going to move. It will just stay there. So what NASA did in 2015, they launched a satellite called Discover. That's a short acronym for Deep Space Climate Observatory. And and they placed it at L1. The L1 point is 1 million miles away from Earth. And it has got multiple instruments. One instrument looks to the sun and observes solar flares and any other upcoming dangers from sun, from solar storms and things like that. And there's another camera called EPIC, EPIC, Earth Polychromatic Imaging Camera, that is looking towards Earth. And the image that you see moving on the bottom left is an image taken, is a bunch of images taken from that vantage point. 1 million miles away, we can see how Earth looks like. And that's the moon that's passing over. So I can share the links. You can go to the website and you can see how Earth looked hourly yesterday or day before that. You get the images right away. I think there's a lag time of 1 day, but it's still amazing that you have a camera sitting that far away looking at the entire of planet Earth. The image on the bottom right is composed from multiple different images from a satellite instrument called VIRS, VIIRS, and that's the nighttime image. You can see a bunch of light up in India. We'll come back to that image. We'll zoom in just to look at how population has grown and how that has affected the night sky or the lighting on the planet. So that was a little bit of introduction about Earth science and our place in the entire universe. So let's get to artificial intelligence, the tool that is being used for almost every domain right now. So artificial intelligence is a machine's ability to sense, learn, reason, act, adapt, just like we humans do. AI is a broader term that describes applications where a machine mimics the cognitive functions typically associated with human mind, such as we learn, we solve problems, or just in general reasoning, decision making, just like humans. It can be categorized into 3 different kinds of AIs or stages of AI, I would say. On the very left, you see weak AI. So it works only on specific tasks for which it is designed for. So weak AI systems won't perform functions beyond their limitations. They will fail. In other words, weak AI is well trained to focus on one single job. A good example is if you use Alexa or Siri or Cortana for Windows. Those are examples of weak AI. Everything that we are doing right now is mostly weak AI. You can train a computer to beat humans at computer or at computing chess, playing chess, or you can train a computer to beat humans at playing Go or any other specific task. So this is all weak AI. It's impressive, but it's still not considered general AI. So the second one is general AI that performs operations just like humans. It refers to a type of intelligence that performs tasks just like we do. And the concept behind introducing general AI is to enable computers to think like a human being on its own. So at this point, there isn't any system that has surpassed human capabilities, but it is reasonable to say that there are plenty of general AI systems that are under research right now. And super AI is what they show in the movies when the AI is more capable and not more, but conscious, just like humans, and they can think for themselves. It's just one step ahead.
All right. So there's a question from somebody, from Ahmed. Question is that how that camera is functioning from such a long time. What's the source of energy does it use to operate?
So that's a great question.
Yeah.
So it was a satellite, discovered satellite. It was built probably a decade before it was launched. It was, I don't know if you know Al Gore. He was one of the presidential candidates, and he wrote the book, The Inconvenient Truth. He was a presidential candidate for United States once upon a time, long time back. So he floated this idea of having a sort of an eye sitting far away and looking towards Earth, and just giving us a view of Earth every hour or so. But because of politics or whatever, this project was shelved. The satellite was packed and put in storage for, I would say, 15 years or so. And then in 2015, they thought that we should probably bring it out and launch it. Very interesting story. So people call it Gore Sat also, after Al Gore. So that's it. That's one of the funny names that they gave it. But anyways, so all the satellites, including this one, they do have some fuel to adjust whenever it goes out of position. For example, the satellites that orbit Earth, they have some fuel that will orient the satellite cameras back towards Earth whenever it goes out of sync. So that is only once in a while. So that fuel is reserved only for corrective maneuvers. It's not used for any other thing.
So
So
are you
for
saying
communication, yeah, for communication, it's the solar panels that are used.
Okay.
So okay. And also for the fuel that is in those satellites, there is 50 to 60 kilogram of fuel that is reserved to bring the satellite down in a controlled fashion so that it does not fall on any inhabited area. So whenever it reaches that point, that's the end of the life for that satellite, and then they bring it down in a controlled fashion. Okay.
Perfect. Thank you so much.
Sure. So we looked at AI. This is a bunch of possible applications for AI. You can create a personal virtual assistant like you have on your phones. You can do natural language processing. We read books, we comprehend news, and then we formulate opinions. Artificial intelligence can do natural language processing and then do sentiment analysis, whether that piece of text was positive and negative, critical, appreciative, or things like that. And you can do multiple different things that are listed here. You can do image analytics, audio analytics, anything that you can do. Robotics, Internet of Things, IoT, and machine learning, deep learning are subsections of AI. We'll get to that in the next slide.
And there is one more question, Makan. I hope, is it okay if I ask it now?
Sure.
A question is from Pooja. Question is, what's the process to work for Earth science in NASA? So if somebody wants to work for NASA, what's the way or process, or what's the mechanism for the same? That's the question. Okay. That will be a question with probably millions of people's mind.
Yes. I would say the first thing is figure out what you want to do for any company, NASA including. Then build your skills according to what you want to do rather than what the company wants you to do. And then once you are good at what you want to do, and if that matches with what NASA does or what any other agency does, you'll find a lot of opportunities. And it's not you don't need to be in the United States. You just need to be good at doing what. I'll go over that later in the slides also. NASA has a lot of collaborations with different countries and different agencies and different private organizations and different non-profit, non-government organizations. So that's one way of interacting with what NASA does. So it's a so what NASA does sort of impacts a lot of people from different domains, which is the positive side, which means like there are a lot of opportunities for you to work with NASA, if not for NASA.
Okay. Okay.
There are a lot of domains that they touch upon, and we will get to more details when we get to the question answer session.
Oh, wonderful. Wonderful. Thank you so much. This was very insightful.
Sure. So again, artificial intelligence is a broader field. It's the ability to sense, learn, reason, act, adapt, just like humans. Then the subfield of machine learning is the ability to learn from data without explicitly programming for that specific task. The performance of machine learning algorithms or programs improve with more and more data. So machines learn from data. That's machine learning. So deep learning is a further subcategorization or subfield of machine learning and AI. Deep learning is when you do machine learning, but you use the multi-layered artificial neural networks to adapt and learn from vast amount of data. And the reason it's becoming it became more and more popular in the last decade or so is because of an increase in compute power and increased availability of data. Because deep learning is number one, data hungry, and number two, computing resource hungry. And we can go over more differentiation, but I'm pretty sure CloudX Lab, they have great courses on AI, machine learning, and deep learning. So we'll try to skip this one. And we'll come back to it if we have any questions. So I'll just differentiate a little bit between machine learning and deep learning because it is sort of relevant to earth sciences. Machine learning is a little bit older field. You have input data, you do some feature extraction, you do some domain knowledge based or statistics based extraction of features, important features from the input data. And then there is a lot of expertise and subject matter expertise and manual labor involved in feature extraction. And then you use classification algorithm to categorize the input into some output. For example, in this problem, it says input is an image. You do something, feature extraction on a bunch of images. Then you use the classical classification algorithms, and it will tell you whether it's a car or not a car. Deep learning, on the other hand, just needs input and labeled output dataset for training, and it will do the feature extraction part and the classification part as part of that deep neural network black box. That being said, that does not mean that you cannot prepare the input in a better way for deep learning algorithms to be able to more efficiently and more effectively do the task for you. We'll come back to that. So that's called feature engineering. So if you have some domain expertise, you can modify the input or reformat or restructure the input data in such a way that it makes deep learning more efficient and effective. And that's specifically true for earth science data. You cannot just simply use off-the-shelf deep learning models and provide it with input and expect it to work just like it works on normal imagery. There are some huge differences between regular imagery and the imagery that is collected from 400, 500 kilometers, 600 kilometers up in the sky. So even though the talk is on AI in Earth Sciences or AI for Earth Sciences, we will try to focus on the deep learning segment because that's the most important these days and the most effective these days. I can take questions if there are any questions.
All right. All right. So wonderful. Thank you so much. I'm really enjoying the discussion so far. First question is that are thermal images captured by this satellite also used for AI interpretation and related to carbon emission?
Yes, that's a really good question. I can probably spend an hour just on that.
Okay.
So satellite images, satellites are just vehicles. They have cameras on it. And those cameras are special cameras. They are not our cell phone cameras that will just take a regular color picture. If you are familiar with the electromagnetic spectrum, you'll know that it goes all the way from microwave to visible spectrum, and then beyond violet, it's ultraviolet, and below red, it's infrared, and then beyond. There is microwave. There are satellites that do microwave also, specifically for soil moisture and things like that. But to answer your question, these satellites, the cameras on them, they are specialized to do multispectral imaging. The reason to do that is what we see with our eyes is red, green, and blue, or the visible spectrum. So satellites, if they can see beyond that spectrum, then we can infer a lot of important information. For example, if you just have a camera that can do red, green, blue, and also infrared, just by adding one band, you can do a lot of cool things with vegetation, studying vegetation. Because infrared is really good at sensing when the plants or the crops or the trees are stressed. By stress, I mean whether they are infested by some bug, or are they not getting any like proper nutrition, plants or crops? Do they need fertilizer? So infrared can see that. So if you combine infrared band or infrared image with red, green, and blue, you can tell if a crop is going to die out before human eyes can figure that out. You will see that to human eyes, it will look like it's just green. To a camera that has infrared channel on it, you can see that it's stressed out, and you can do something about it before it actually affects the crop in a very, very negative way. So I hope I answered that question.
So the other question is from Fayaz. Question is, from when can we start preparing for NASA?
I think like everything that you have done so far, I think you must have prepared you in some capacity for any job, including NASA. So everything you have learned, you learn every day. I'm still learning at this stage. So if you are a lifelong learner, so it does not matter whether you are preparing for NASA or whether you are working for NASA, you will continue to prepare yourself for NASA or any other job.
Okay. There's an interesting question from Vinay. How we implement machine learning and deep learning in satellite communication systems? I'm guessing that the process would not be much different, is it? Or is it very different? Like in terms of power consumption, in terms of, because I think in satellite communication systems, the power would be one very important, power consumption would be very important aspect, isn't it?
Mm-hmm.
So,
Yes.
so yeah.
Yeah, so satellite communication, if you're talking about actual communication, like cell phone communication or internet through the satellites, like Starlink is doing, that is Elon Musk's company, they are already using a lot of AI to beam those signals to your home if you have that satellite dish from Starlink. So what they are working on right now is satellite to satellite communication. So how Starlink works is it's a communication satellite. All other communication satellites are just your home dish TV and cell phone and satellite phones and things. But the cutting edge in satellite communication, I would say, is providing internet through satellites, and it's coming to India also. I think by the end of this year, or maybe next year. Next year. So what they are working on is they are already using AI to do. So how Starlink works is they have some ground stations. They have a bunch of satellites going around Earth. Those ground stations take the internet from the fiber optic cables and then beam it up to a satellite, and then that satellite beam it back to your specific home. And the receiver at your home, it's a phased array antenna. Those of you who are familiar with Air Force or something, they'll know that the fighter planes use phased array antenna. So what that does is it's an array of antenna, like bunch of antenna, and then they use algorithms to communicate with the satellites that's overpassing. So once that satellite goes away, the next satellite comes in, and the phased array antenna. So the whole dish antenna doesn't move; it just stays like this. There are micro antennas, like smaller antennas inside that, and they sort of sync themselves with the satellite, and though they move with the satellite, and then the next one comes, and then they do that. So that's how it works. So what they're trying to do now, so you'll probably understand if you understand if you understood what I said just now, that you need a ground station. It beams that signal to Starlink, and the Starlink sort of reflects that back to your home. So what they're trying to do right now, so with this approach, you will need a bunch of ground stations around the world. So what happens if you want to beam internet to North Pole? There is no ground station close to North Pole. So what they're trying to do is they're trying to beam that signal from the ground station to one satellite that can throw that signal to another satellite, and that signal can go from that satellite down to North Pole or to the ocean or middle of nowhere, anywhere, right? So they're working on that. So the need of they will need minimum ground stations. So for that, they are using a lot of artificial intelligence algorithms to figure out the closest satellite in the network and all those things. And there is a cool website that depicts all the satellites passing over your house. You can put your latitude, longitude, or your position, or your city name and all, and it will do it for you. It's really amazing. Yeah.
What's the name?
I'll share the link. I don't remember. It's third party. It's Starlink didn't make that.
I see.
Some guy from Europe did that as a hobby project. It's really cool. They have a Docker image for that. You can just run that Docker image, and it's
Okay.
really cool. We'll get into
Wonderful, wonderful. There is another interesting question. Question is how to choose model for satellite data. What about feature selection and extraction? Yeah, that's a question from
that's
somebody. Yeah,
so
Chris.
that's a very that's a very good question.
Okay.
Uh,
It's okay. I'm
okay.
actually enjoying the Q&As more. It's very informative.
Okay, perfect. That's good. That's
Okay.
great. Okay, in that case, like if we go longer, we can merge the Q&A time into this one. So whatever
Yeah.
minute you want to go.
I think let's keep it more interactive. And I'm really
Yeah.
happy that there are 82 more than 82 people watching from the beginning. So it's really it's total fun, and I mean I'm finding it very informative right now. Okay.
That's great.
So a question is how to choose model for satellite data. What about feature selection and extraction? And Also, Dr. Makhan, in case there's something, you know, feel free to say that no to a question in case something you
No,
don't want to share. Okay, it's completely okay.
no, it's just the time issue. I'd love to chat and answer every
That's
question
okay.
and spend
That's okay. So
spend time on that.
yeah, don't worry about the time. So we'll
Okay, all right. So yeah, so first step is data collection. You don't have to worry about that. Deep learning, as I said, is a very data hungry framework. You don't have to worry about data collection because NASA, European Space Agency, Japanese Space Agency, Indian Space Research Organization, they have spent decades collecting data for you. So it was just waiting for the right time. So I don't think there's any field other than earth sciences that is as ripe for using deep learning processes and deep learning algorithms. Anyways, data collection, you don't have to worry about that. I'll go over that in the next couple of slides, where to get data, how to get data, and all those things. Data preparation, that's an important step. That's where you will need, actually there is another step before any other step. That's step 0. That's to understand if the problem that you are trying to solve
Makan. Yeah.
lends itself to deep learning.
Um, sorry to intervene.
Go
There are
ahead.
a couple of questions. I think let's go with the questions.
Okay.
Yeah, I think, see, the thing is that there are lots of people on this channel who actually go through all of this, and this they can find, you know, elsewhere. But the Q&A and everything is something that they won't find anywhere
Okay.
else. Yeah.
Okay. Great.
So,
Great.
and I also, I'm loving the answers, and I'm having this
Okay. Perfect.
something, a lot of new things I'm learning. So
Okay.
question is how to choose model for satellite data.
Okay.
What about feature selection extraction? Okay, I like to add
Perfect.
here. So what the point that you just showed in the previous screen, it was about that instead of we doing the feature selection, we are delegating it to the deep learning so that we don't have to
Yes.
do feature selection and extraction, right?
Mhm. Mhm.
And yeah, I think that's one of the biggest differences between the classic machine learning and today's deep learning techniques is instead of we ourselves coming with all kinds of features and representing data based on our experience, we let the neural networks and the complex techniques decide all of that, right? Makan,
Yes.
is my
Yeah.
interpretation correct?
That's very correct. Yes. Yes.
All right. There are a
But I'll
couple.
add to that
Okay, please go ahead.
that the effort that is traditionally spent on feature engineering or feature extraction
Mhm.
for earth sciences, you spend the same amount of time. I would say you should spend the same amount of time and effort and energy in data preparation. By data preparation, I mean there is a lot of cleaning up for satellite images. You have to remove the clouds. You have to get rid of any noise that's in those satellite images. And because what the human eye see is just an image, what um, the computer is seeing is numbers. So there might be some weird noise in those numbers that will make sense to the deep learning algorithm or the computer. It will think that there is a pattern there, but there might be not be a pattern there. For example, if you're familiar with the synthetic aperture radar, SAR. So SAR is another type of imaging. It's not red, green, blue, infrared. It's just in a different wavelength. So SAR is active. So the satellites send out a certain frequency. It hits the objects on ground, and then it comes back, reflects back. It's called backscatter. So backscatter, by virtue of the technology, it has a certain error, not error, sorry, certain kind of noise. It's called speckle. So if you take SAR image and try to look at this, look at the SAR image, you can see a little bit of graininess. But if you feed that image directly to a model, that speckle will have a very profound effect on what the computer is seeing. Humans, they won't see much of a difference between a speckled image and a despeckled image, but computers will just go crazy. They'll not know what to do. So data preparation, you have to know that if it's a SAR kind of image, you have to do despeckle. It's a very, very important. It can be a difference between uh, making sense out of the image and then or just getting nothing out of the image through no matter what kind of model you choose. And the question about choosing the model, again, it depends on what kind of image it is. If you are using off-the-shelf models, it depends on how deep you are into deep learning. You can design your own framework, own model just for satellite imagery, because satellite imagery is different. It does not have 3 channels. It has more than 3 channels because it looks at different um, windows from the visible spectrum and the non-visible spectrum also. So the traditional models are based on red, green, blue imagery, 3 channel. So none of those will render itself to be used for Earth data imagery unless you limit yourself to using 3 bands or 3 channels at a time from hundreds of channels that might be available from a satellite camera.
Okay.
So,
okay. Wonderful. There are a couple of more questions. Okay.
Yeah.
I think we can take questions. So question is spectral imaging also used in these projects? Is hyperspectral
Yes.
imaging also used in this project?
Yes. So for those of you who don't know what hyperspectral is, normal camera on cell phone or a digital camera is 3 channels. It has got 3 spectral channels. That's what it means. Spectrum is the entire electromagnetic. And yes.
So do you mean to say that 3 channel means like color, right? Red, green, blue, those 3 colors?
Yes.
Okay.
Yes. Yeah.
Okay.
Spectral is hyperspectral means hyper, which means it's not only 3 red, green, and blue. It's hyper. It means like it has 50, maybe 100. Who knows?
Okay.
Right.
Wonderful. Wonderful. Yeah. All right. That means the way you design convolution neural networks is completely different.
Yes, you can have a satellite camera or satellite image that has 100 channels.
Okay.
And that is called a hyperspectral image.
Okay.
Even the red channel is not a red channel. It could be red can be split into like 3 different channels, because red is not a single frequency. Red is a range of frequency. Green is a range of frequency or wavelength, right?
Okay. Okay. Wonderful. There's one more question. Question is, can we also access satellite data and do our own research? I think I remember your previous project earlier, right? A couple of years ago, you had built a website for the accessing data, right? So
yes,
the question is that can we also access the satellite data and for our own research?
that's a great question, and that's why I am here, why I am doing this talk, because all of this data is available for the past like so many decades. You have lots of data, and it's all available for free. And I'll go over where you can get that from. There are APIs, there are pre-processing algorithms written for you. You just need to have time and knowledge on what to do with the data and what problem. And we'll also go over like what kind of problems you can solve. You don't need to necessarily work for a space agency to help planet Earth. You can just sit in your home and you can make some profound discoveries and insights using this data and the knowledge that you can acquire from all the things that are available online and from CloudX Labs courses and things.
Wonderful. I'm going to post one question. There actually lots of interesting questions are coming in. Okay. One question is, it is interesting to know how the satellites capture the information of the Earth. That means which tools, okay. Which tools make it possible? Okay, that's a question. What are those tools that make it possible to capture the information of Earth for satellites? That's the question. Yeah.
Uh,
I mean, there's a
all the information.
continuous question on it. What are the tools, technology, and softwares required for it? That's the question.
Sure.
Okay.
So when a satellite is designed, before the satellite is designed, there is a science question that you are supposed to come up with, like what is the science problem, what is the science question, what's the problem that you are trying to solve. And based on that problem, they create a science team which is composed of scientists, engineers, professors from different universities, not only from the US, from all across the world. That's for NASA. For European Space Agency, similarly for ISRO, Indian Space Research Organization. So they come up with a science question, then they figure out what's the best way to answer that question. What kind of instrument do we need? Can we just strap a Canon camera on it and it will do the thing? If it can take red, green, and blue images, maybe it can do. Then they figure out, oh no, we have to study the forest, we have to study the crops, we might need the infrared channel also. Okay, strap one more camera, or just make a hyperspectral camera. So those are the tools and technologies. And in terms of technologies, they will think, okay, now the hardware is ready, what is the software that is going to run the hardware up there? And oh, before the hardware is ready, they'll see that, okay, the hardware is going to be exposed to all the solar radiations. There is no atmosphere to protect the satellite and the instrument from solar radiation. How do you protect against solar radiation, solar flares? Is the satellite going to go up and the electronics is going to be fried in one single day? They don't do that, right? Or is like there's a lot of other components. They do the testing on the hardware, whether it will survive the launch, because when you launch the satellite on a rocket, the rocket has lots of force and vibration and things. So they test whether it's not going to break apart on the way. And then they look at all the fuel requirements, how long they want to study, how much fuel do we need. So that makes the payload heavier. What kind of rocket we need to launch it? What kind of technologies, what kind of software do we need to, what kind of operating system the onboard motherboard will have that will be resilient to startups and restarts, and can we program it from Earth using the communication? Then the communication part comes, and all the things. There are a lot of things.
Wonderful. Wonderful. There are quite a few questions. I hope you wouldn't mind. These are very wonderful, people are really liking the discussion. A question is, when do you capture or update a Google Map Earth image?
So
Basically,
Google is a private company.
So they get the data from who? I mean, Google and other people.
Okay, Google, I think they used to buy the satellite data, because NASA data and all other space agencies, European Space Agency, Japanese JAXA, JAXA, those data are free, because that data is captured using the taxpayers' money, so it's citizens' data.
Okay.
So Google is a private company and they need high resolution maps.
Okay.
For that, there are a lot of private companies that have launched their own satellite, and one is called Digital Globe.
Okay.
If I'm not wrong, I think Digital Globe have a very high resolution, a bunch of very high resolution satellites, and I think Google bought Digital Globe or something, or they used to buy the images, definitely, but I might be wrong. But I think they bought a bunch of satellite companies that have their own satellites. So Google might have their own satellites up there too, but they do private. There are a lot of private companies. There is a private company called Planet. It used to be called Planet Labs. It's only like maybe 5 or 10, 8 years old, maybe 8 years old. Planet Labs, now it's called Planet, and they have these CubeSats, which are the size of a shoebox, and they have a bunch of those in the orbit, and they can do a 3-meter resolution image or video of any place on Earth. They sell their data to journalists and news outlets and things like that. So there are a lot of private and public companies.
Okay. Next question is, when we talk about prediction of climate through agriculture-based satellite, how we can implement AI in those satellites with real-time data if we have started it with implementation of ML? I've also
so yeah. So most of the satellites that are up there that are serving the agriculture community, they might have some sort of AI built in. Landsat 9. This image on my uh, right here is from Landsat 7, all these images. But Landsat 9 was launched maybe 10 days ago or maybe 2 weeks ago. So maybe the newer satellites do that. They might have some component in there, but I'm not aware of any satellite that are doing active AI up there, because one of the downside of AI is compute power and power resources. So how do you handle that in space with just your um, solar panels? It's not very easy to do that. So maybe uh, I attended a talk. I forgot what the company was called. It was a private company. They said that they are working on ARM-based processors that are less power hungry to do edge AI in the satellite itself. So it can do some processing up there and then only beam us um, the gist of what it sees. But I think the old-fashioned way of just letting the satellite beam all the data down and we doing all the AI-based processes here on Earth, that is still the most prominent one, but maybe that will change in future. I'm not aware of any satellite that is doing implementation of ML in space.
Okay. A question is, how much time does it take for the whole process, whole purpose? I mean, the whole communication process of Starlink satellite. Basically, okay, all right. So should I?
Yes, so Starlink is a private enterprise. It's Elon Musk's company. Uh, if you're talking about like what's the delay, I had Starlink for a couple of months. I used it. It's pretty good, but when it switches satellites from one satellite to another satellite, I used to drop my Zoom calls and my video streaming things. But if you're doing Netflix or YouTube, the things that can buffer, it was working wonderful. But if it's real time like this, anytime the satellite used to go away and the next one comes in, there was so in the entire day I used to have like 2 or 3 dropouts. But you're talking about the latency, the delay. If you're talking about the time, there was no substantial delay. I don't remember the number of like milliseconds it had the delay, because the base station, the ground station beams the internet to the satellite and then it comes down. So there is some delay, but they are working on reducing that delay, and maybe that's where the AI comes in. But it was the lowest in terms of, because Starlink satellites are in a low Earth orbit, also called LEO, L-E-O, low Earth orbit. And that's why it's much better than other satellite communication or communication satellites, which are way above the LEO, low Earth orbit. So that's the advantage of Starlink. It reduced the latency to like a few milliseconds.
Okay, all right. There's a question from Rupin. Question is, can there be machine learning AI which can understand the problems associated with Earth and give solution by its own without asking question to the machine? All right. Machine
Yes.
is the AI.
Yeah.
That's all.
Yeah, I think I understood it. Rupin, yes. For example, some problems are easier than others. So it depends on what problem you are trying to address. One easy problem or not so difficult problem is to figure out where the forest fires are. You might have heard like there is a lot of forest fire in the past couple of months in California, and then there was bush fires in Australia a couple of
Yeah.
years ago,
Yeah.
2 years ago. So those kind of things that are very, very hurricanes, you can just look at the image and the machine can figure out that there is a hurricane or a tropical storm forming somewhere in the Atlantic, and that will take the form of a bigger hurricane. So those kind of problems, yes, you can train the machines to do on their own, and they alert us before it even happens. Yes, possible.
Next question is to me. Are you going to bring any AI machine learning course to earth science domain? We are thinking in the other way, though that's on my mind to bring in one course onto like earth sciences. But the way I'm thinking is that instead we will introduce it like a short-term course, which will complement our big term course. That's how we are thinking about. Like we'll take probably 4 to 5 earth sciences problem and walk through how to solve like 4 or 5 different domain problems and then try to solve them. And I think that will be a better approach. And that's something that we will work upon. And a question from Kirti is, as a startup in AI, how can I provide services regarding earth sciences as a domain, as the domain is very vast? Um, okay, it's an interesting question. Question is that, I mean, as a startup in AI, how can I provide services regarding earth sciences as the domain is very vast? Okay. Uh,
Okay. I think there's a if you read your question again, Kirti, the answer is in the question itself.
okay.
You say like the domain is very vast and the startup in AI. So maybe it's time to have a startup in earth sciences rather than AI and use AI as a tool, or at least have a division or a section in your startup totally dedicated to the domain of earth science. And I'll come to an example of something or someone who has done that later. So understand earth science. So earth science should be the focus and AI should be the tool, and identify what problem is close to your heart or close to the community that you are trying to serve. It's a very human issue, and there are more than one issues that are affecting humanity right now. You can pick any, and you can just go places, no matter which one you pick, and we'll come to those problems. You can pick any of those. I'll come to that in a couple of slides, maybe 2, 3 slides.
There is okay, very interesting questions. Question, let me just post it here. I think question, what's the relationship between AI and remote sensing? I noticed most of your discussion is centered on the EM spectrum and its relationship in acquisition of the data. Uh, so, so the question is, what's the relationship with AI and
Yes.
remote sensing? Okay, please.
So remote sensing is just a process of collecting data. AI is a tool that will use that data. The final objective is to address the problem that affect earth sciences. So the problems come from we living on planet Earth and exploiting the resources. Those are the problems. And we use AI and remote sensing as tools and data collection mechanism to solve those problems. And we'll come to that.
A question is, how does quantum communication use AI in its mechanism, and how about the principle applied herein? Okay.
Gladys, I'm not sure if I understand the quantum communication part. If you can expand on that, we can come back to that question again.
Okay,
is it quantum computing?
Yeah. So I had a talk by this professor from quantum communication, quantum mechanics. Okay. So essentially, the quantum computing, basically one of the biggest use case is quantum communication, in which the idea is to be able to transfer data that fast that can be handled by quantum computers. So there's the only definition I know. I'm also pretty blank when it comes to quantum computing as of now. And yeah, so probably it'll be better to ask Dr. Dimitris Angelakis, who gave a talk. So, all right.
Yeah. So Gladys, I'll probably try to attempt to answer your question. So as quantum computing will become more commonplace, there are companies like D-Wave and other companies that are actually creating computers that will be in production soon for normal public use, or for I think Google or Microsoft, one of them, they have an instance that you can request and use for free just to do some quantum computing. I'm not sure, but I can explore that further and answer that. And Sandeep, he can convey that to you. But if and when quantum communication and quantum computing become more popular, the way we will, it will open up another tool or tool set, just like artificial intelligence and deep learning have opened up a lot of avenues. We can probably throw more data and expect more versatile results, and use more efficient algorithms using quantum computing when it becomes more commonplace.
Okay. Okay. The next question is it possible for AI to predict the various rock types or minerals in a particular environment, thereby preventing the conventional field mapping as carried out by geoscientists?
I think the question is not for AI to predict. It could, what you meant is for the satellites, AI to use satellite imagery to predict various rock types.
Okay,
What
yeah.
you see from satellites, satellite imagery, maybe drones can help, because satellites are so far up there, their resolution, there is a limit on how fine or how coarse they can see from up there.
Okay.
You can detect subsidence, like different rock structures, or different tectonic plate movements and things, so like very micro movements, from using like SAR and synthetic aperture radar, SAR interferometry and things like that. But to identify rock types, unless it's a vast expanse of the same type of rock, it might be a little bit difficult to do using satellite imagery, but definitely possible using remote sensing, because remote sensing is just sensing something remotely. That can be done from aircraft, drones, quadcopters, satellites, helicopters, any of those things. So yes, that's possible, but it depends on what we are trying to do with that. Minerals, they do some sort of oil and gas industry use satellite imagery to scout areas that might be productive for gas and oil exploration. So I'm pretty sure it is doable for some sort of minerals, depending on how far deep in the earth they are, or are they on the surface. Satellite only see what's on the surface. Microwave can penetrate a little bit, couple of centimeters into the ground, just to detect moisture and stuff. But anything that's hidden below the crust, satellites can't see for now. They don't.
Okay, wonderful. Another question is, how are satellites used by GPS for GPS?
GPS satellites are basically a constellation of, if I'm not wrong, 23 different satellites. They are basically very accurate, super accurate time clocks.
Okay.
And depending on like how and when you get the signal from different satellites, so at different GPS satellites, so out of those 23 or 24, I think 23 is the number, 23 satellites, at a given time you should be able to get at least 3 satellites to triangulate your position based on the accurate time clock on those satellites. I think that's how it kind of triangulates the exact position of the person who is receiving signal from 3 or more satellites. And it does take Einstein's relativity into account as well.
Oh, wow. Okay. There's a question how spirituality is connected with AI. Honestly, I'm not an expert on that, but I would not comment. Would you like to say anything?
No, I think in one of the slides I said like AI is different kind of AIs. We are still in the very initial stage of artificial intelligence, and consciousness is like too far away from that, where machines will make decisions on their own based on their own moral compass or whatever. So it's probably outside my expertise as well.
Okay. All right. So there's a point that let the session go. But my point is that I think this discussion is really helpful, and I'm really thankful to to Makan to give this much time for us, because most of the theory is whatever we're going to talk, you can always find it online. But this discussion is something that you won't find online elsewhere. So I think that's why I requested Dr. Virdi for giving more detailed answer. All right, go ahead. I think, yeah. So,
Okay, coming back to Earth. Earlier, we looked at Earth sciences and its subsystems, the atmosphere, hydrosphere, biosphere, cryosphere, geosphere, and all those things. So let's discuss how human activities are impacting these subsystems, the natural processes, and how artificial intelligence, or in fact, deep learning, can help us understand these impacts, the human impacts on these subsystems. So that we can make decisions that are better for the planet's future. Let's go there for a moment. So as of now, or maybe mid of last year, the human population is 7.8 billion. And according to various calculations, the highest possible number for a sustainable population on the planet is 8 billion. What I mean by that is, if you have a ship and ship can fit only 1,000 people, if you have 1,001 person on it, it will be struggling with the resources that are on that ship that is floating in the ocean. So we are on a spaceship called planet Earth, and the capacity is 8 billion according to a bunch of calculations. We are already at 7.8 billion, and we will be reaching the 8 billion population by 2025. So which means that we will be overpopulated by that year, and that means it is going to have extra stress on the natural resources. Just to give you an idea, it took over 2 million years of human history for the world population to reach 1 billion people. 2 million years to reach 1 billion, and only the last 200 years to reach 7 billion. So 200 years to 7 billion versus 2 million years for just 1 billion. So to support this growing population, humans interact with natural resources, or interact with planet Earth for getting the natural resources for food, water, energy, land, and these are a bunch of the sectors where humans interact. Agriculture, growing population need more food, urbanization, for shelter, then we need water, for food and shelter both. We need transportation for mobility. For energy, we need mining and other things, right? So environment problems associated with the extraction of these natural resources, they may shift to some other countries who are doing which are doing the actual extraction and processing, but the global impact of the consumption will keep on increasing, right? So if you look here, that's a satellite image of Earth at night. The one on the left is 2012, one on the right is 2016. If you just look at Delhi, New Delhi area, you'll see how a bunch of light has come up. That's also because of electrification, but it's also the growth of population. There is some correlation between the two. Also, these images you can also get. It's on a satellite called, it's on the instrument called VIRS. It's on board a satellite called SPSS. So just to give you a life cycle of extraction of natural resources, there's extraction happens. There are emissions, or by emissions I mean pollution of from the equipment that is doing the extraction. Raw material is extracted from that. it takes energy, then again emissions. There is production from using those extracted natural resources. Then you make products and services out of that and move them around, transportation, that's again emission. Then there is consumption. When you consume those, then again there is emissions, and then there is waste. Then you process the waste, and then there is again some emission. So anytime the population grows, it's going to have some sort of stress. And even without the effects of climate change, growing food demand and growing population will require greater energy and water inputs for agriculture. And water is getting more and more scarce. Supplies and scarcity of water could mean greater energy use for desalination. If you are trying to use ocean water and try to use it for drinking, you will have to desalinate, remove the salt from it. That's a very energy intensive process. Where would that energy come from? It will be from the natural resources, and that will again create a lot of emission. So it's a vicious circle. And this also means that the land that could be used for agriculture will be used for production of biofuels and for urbanization and things like that. So there was a paper recently, I think early this year, the study published in Nature Climate Change journal. The researchers found that the anthropogenic climate change, or you can say the human caused changes, have reduced the global agricultural total factor productivity. Basically, the global agriculture productivity have decreased by 20%, 21% since 1961. Which means that we are losing productivity in the agriculture sector, which is equivalent of the growth for 7 or 8 years, 7 years. So these changes were substantially higher for warmer regions like Africa, Latin America, which is South America, and the Caribbean. So these results are alarming because they show how climate change is directly impacting global food security and economy in general. So this is a map of our impact, which is becoming harder to ignore with each passing year. Our cities, infrastructure, agriculture, pollution are all forms of stress that we place on planet Earth. So this is a map from David and others. It shows just how much of the planet we have modified. This research estimates that there is 18.5 million square kilometer of land area that has been modified. That's a lot of area. So in this image, the darker regions are modified less, and the lighter regions, or the reddish and the purple and the yellowish regions are the most modified by humans. You can see India, it's all lit up. And you can see that the darker areas are not used anyways. There is Greenland, it's ice all over there. Middle of Australia, it's all desert. And north of Africa, it's again the Great Desert. And if you look at Canada or Northern America, it's again all tundra. It's all frozen area where no one lives. So basically, wherever we live, wherever we could live, we have really exploited and modified. So what do you mean by modification? There are built up areas. There is agriculture, energy and extraction of resources, which is mining and stuff, power plants, transportation, logging, which is the wood industry, cutting down of trees, deforestation. And then there is a human intrusion with the large urban areas like New Delhi, and natural system modification, which is modification of the river systems by putting dams on it, or when you build a city around a river, the chances of flooding increase because after the rainfall, the rainwater does not is not absorbed by Earth. It's there's a lot of impervious areas with the parking lots, with the brick and concrete buildings, with the parking lots, and with the roads and infrastructure. There is less area that will absorb that water. So all the water from the city will go into the sewage system and then into the rivers, and the effective flow in those rivers will increase because of urbanization. Pollution is another phenomena, bringing acid rain and fog and smog for those of you who are familiar, who are living in New Delhi or any other bigger metropolitan cities. So these are all the different ways we affect. So there are a bunch of images of what we are doing to the planet, and these are all opportunities for solving or at least trying to understand using all the tools that we have available, including the AI. There is forest fire on the top left. In the middle, again, forest fire zoomed in. Then there are hurricanes. Last year was, I think, a record-breaking number of hurricanes that affected United States. At the bottom left, you see India Gate, New Delhi. The picture on the left is the smog. On the right is a little bit clear. It's affecting the health of people in those metropolitan areas. Not only those who are alive, but also for those who are not born yet. So there is an increased pre-pregnancy mortality that is happening in Delhi and the areas, and an increase in people with asthma or the hospitalizations related to asthma. Then the next one, this green picture here, is flooding along Brahmaputra River in Bangladesh. And the next picture here is dust blowing. You can see that that is the coast. And these plumes that you see is actual dust blowing off the coast of Pakistan and Iran. That's towards the Indian Ocean. It's blowing south towards the Indian Ocean. And the right picture, it's not very clear, but probably you can see it's a map of India. Here is Gujarat, and this big red blob is New Delhi, and this is all Uttar Pradesh and the related areas. So the darker pixels, the red pixels, mean there is a higher index of aerosols. Aerosols are small particles suspended in the air that enter our system through the nasal passage when we breathe. And higher aerosol index means, so those particles are really tiny particles, 2.5 microns, 10 microns, and they affect your lung capacity and in the long term, the life expectancy. So very, very, these problems are very close to human health and the future of the planet. So how can artificial intelligence help? So this is where we tie the two topics together, the introduction to AI, or deep learning in this case, and an introduction to planet Earth, what we do to the systems, the subsystems of planet Earth, the processes. Even though we study those processes separately into 5 different categories: cryosphere, hydrosphere, geosphere, atmosphere, and biosphere, they are all interconnected. They are just separated to understand them better. They are all connected though. In the similar way, artificial intelligence can is a field, is a tool that can interact with either one of those 5 subsystems or a combination of those. The end goal is to not use AI to solve hydrospheric problems or to solve atmospheric problems. The end goal is to solve planet Earth problem, because all these processes are interconnected. So use of AI to solve Earth science problems. And if you're trying to solve air quality problem, you might need to use a lot of land-based data. You might need to use a lot of river-based data, the pollution data, the transportation data, the emission from transportation, the emission from energy sector, emissions from agriculture sector. So how can AI help? One, there's a large amount of data, really. I think Earth data or Earth science data qualifies as big data from decades ago, when big data was not even a term or a buzzword. So you can process large amount of data that has been collected for the last decades effectively and very efficiently. A human will take years to sift through or go through all the data that is available. So when AI is applied to large data collections, such as the one from NASA's Earth observing systems, AI and ML, like these technologies, can be used to sift through years of data and imagery rapidly and efficiently to find relationships or interconnections or processes that would be impossible for human to detect. So second, it can identify, like I said, complex patterns and detecting phenomena that might be difficult for humans to understand or find the causal relationships between, the interconnect between. The third is once you do 1 and 2, you can make better decisions, and not based on politics, not based on your personal beliefs, but on data. It's data-driven insights that come from processing this large amount of data that's available for free, mostly for free. And the fourth one is the actual. So 1, 2, and 3 is just we doing our homework. 4 is where it drives the point home that you take this data, you run it through process 1, 2, 3, and then you make an actual impact. You make policies based on that. You stand up for a cause that is on a planetary scale, and then make your opinion based on that, and then have a real impact on the life of not only the planet, but also the future generation. And with that, we can get to the actual data collection part. And before that, we can stop for either a break or some questions.
Yeah, we can take a couple of minutes break, maybe 2 minutes break, whenever you're back. So, all right.
Yeah.
All right. So yeah. Thank you. We are taking a break for a couple of minutes. We'll be back in 5 minutes. Thank you, everyone.
Okay, thank you.
All right, so I'm back. Hey everyone, so please feel free to ask questions. This is a great time and great opportunity to ask questions to Dr. Virdi. It's going to be quite useful. Oh, we were on the break that time. That's why the screen looked hanged. Okay. So I'm really happy to have such a great audience today. Looks like the satellites are really, really interesting to many people. All right. So Dr. Virdi is joining us in a couple of minutes, and feel free to ask your questions using the comment box. I mean, both Dr. Virdi and I would love to answer your questions. All right. Wonderful. I think he's also back. So feel free to ask your questions. This is a great time, and we really enjoyed your questions. And looks like the satellites are way more interesting than the AI. And as a matter of fact, it is, because my kid and my wife are also attending this session in another room. And that's a interesting part about it. All right. So yes, we were on a break. That's right. For a couple of minutes. Now we're back. There is a question from Abhishek. Is satellite data also captured from other planet for some analysis or for the model?
Yes, there are satellites around Mars. There are satellites around Moon, and there's one satellite around Mars from Earth, from ISRO from India. So Mars orbital mission that is going around Mars. I don't know if it's still functional, but what's the life of that one? But yes, there are satellites around other planets and satellites around satellites, which is around Moon. Moon is a satellite.
There are a couple of more questions. Okay. I think I'm really loving the answers, and actually this is way more interesting. Okay. A question is that how can we get Earth Sciences data and how to use the data? So I think Mark can go ahead.
Yes, that's what this slide is about. So we can get to other questions if there are.
Okay.
Before I dive into this question from Abhishek.
Perfect. Let me. There is one more question. Okay. Question is from Sudarshan. Question is: can we use hyperspectral imaging in AI for finding minerals using deep learning techniques?
Hyperspectral imaging in AI. The question is, if you can do anything with the data without AI, you can do it with AI also. So the question is not whether AI can use hyperspectral imaging to find minerals. The question is, in general, can hyperspectral imaging be used for identify minerals? And I think there was a similar question earlier. And now that I think of it again, what's the name of the satellite? There is a satellite that's already doing that. There are a lot of dust storms from Africa.
My question here is that when we say hyperspectral imaging, does it always mean that the imaging is done from the satellite, or it could be a normal camera as well, right?
No, those cameras are built here by different companies. You can take that camera in the field and take hyperspectral image of your tree or a human, if that makes sense. But those are just cameras. You can strap them on drones and fly it over your fields to monitor your crops. You can do hyperspectral imaging on Abhishek asked a question about minerals, I think, or Sudarshan, I think. Yes. So yes, you can fly it on a drone or a quadcopter or a robot arm or anything, and yes, you can capture those images.
Okay. So these images can be used. Can they be used for finding minerals? Right?
Yes.
Okay.
Yes, I think there was a similar question earlier.
Earlier, yeah.
But yeah, it didn't occur to me. But there was some. Northern Africa, the whole desert, lots of dust storms happen over there, and I am forgetting what was the name of that mission. They used the data for identifying the minerals from those dust storms.
I see.
So yeah, I'll try to find and probably post it, and you can come back to CloudX Labs, and
Yep.
they'll have that.
It'll be this YouTube video is going to be live in public, so we can find it in the comments. Okay.
Perfect.
All right. Wonderful. There are a couple of questions. A question from Abhishek Avasti is, can we analyze Milky Way galaxy? And my guess is that people are analyzing it, isn't it?
Yes. So not only the Milky Way galaxy, which is one of the many galaxies floating around, people are using AI-based algorithms. Even before AI was a thing, people used to use other algorithms. It's basically images. The Hubble Space Telescope sits out there, and it's observing the deep space. And the images that we get back are analyzed using either human eyes or using algorithms. And now that we have all these images from Hubble Space Telescope looking at all different galaxies from far, far away, the AI techniques are being used to look at the shape of the galaxies and other things, the movement, the speed, and all those things. You can analyze a lot of that. And there is one more after Hubble Space Telescope. There's another one, the James Webb Space Telescope, JWST, which is right now, I think it was on a ship. It was shipped last month or so. It has reached, I don't know if it's being launched from New Zealand or somewhere in that region. And it's going to be launched in the next, like very shortly. And it's the next super big telescope, a multi-billion-dollar telescope that was being built for the last couple of decades. And it will get more images of the galaxies and our own galaxy as well. So in the future.
Yeah, that's pretty much for questions. So you can go ahead with the remaining presentation. Please feel free to ask questions, everyone. This is a great time. And there had been very wonderful set of questions. And all right, over to you.
Yes. There is a question from Valeron White. Will there be a niche for AI-based companies in the space industry infrastructure in the future? Yes. Not only space industries, normally they combine the Earth observing with the space, but when they say space exploration, it's outwards from Earth, away from the Earth. What I am more focused on for this talk and also in my career is looking inwards towards the Earth, even though I am very interested in outer space as well. But yes, there is a lot of opportunity there, and it's going to be a multi-billion-dollar industry. And that's the entire industry is going to be maybe like, I don't know, more than like multi-billion, maybe in trillions or something, but definitely multi-billion just for Earth, and even like small segments, just like forestation and the carbon budget and carbon footprint and how companies control their carbon footprint. We'll talk about that. I think there was another question that someone asked earlier about the AI startup and all those. So it's a similar question, and I'll answer that with one example and one actual company that is doing something related to that. And there are a lot of opportunities and a lot of other things that I showed you earlier. All the problems are an opportunity for you to you work on. And all the data is free. You don't have any investment. All you need is a computer and a brain. And you can make a company in your home and do really tremendous things. And it's a big industry in the future. Okay, coming back to the question of data, how can we get Earth science data and how to use this data? Even though I do work for NASA, the data is available from a lot of other agencies as well. So let's talk about the data that is available for free to be used for your analysis and training your AI ML algorithms. So there are petabytes of freely available data from multiple organizations across the globe for studying Earth science. Some of these organizations are NASA, obviously, Indian Space Research Organization, ISRO, European Space Agency, ESA, Canadian Space Agency, CSA, Japanese Space Exploration, JAXA, JAXA, etc. So I'll focus on Earth data available from NASA. And maybe a little bit later, we'll also talk about data that is available from European space agencies. And these agencies, they do collaborate, and a lot of their data is available from one and other. Okay, so before I go, so this is basically a timeline of all the different satellites. Lots of satellites after 95, Landsat 7, Terra, Aqua, Aura, CloudSat, Calypso, all with different science objectives. The night sky image I was showing you, so can you see my mouse cursor?
Move it. And
do you see it? Okay.
Just
so if you look at the image,
yeah, I can see it.
That's all right.
I can see.
Okay, so so if you see this satellite Suomi NPP, so that is the satellite that carries that instrument called VIRS, VIIRS, that creates those nighttime images. So these are the names of the satellites, and they might have instruments, which is basically cameras on those. So one satellite can have multiple cameras, and they all can do like different science, because it takes a lot of money to launch a satellite. So a lot of different science objectives, or those instruments that are studying a specific science, or studying a specific science question, or answering a specific science question, they get together and they say, okay, can we strap our camera on this same satellite as well? So the cameras are called instruments. They create their own data, and the vehicle is the name of the mission, which is the satellite. So in this case, is Suomi NPP. There are multiple instruments on it. VIRS is one of that. And I worked a lot on Terra. If you go to this year 2000, there is TERRA, Terra. So Terra has multiple cool instruments. It was launched in 1999, and it was supposed to be up for 5 years or so, but it performed so well that maybe 7 years, I think. And since 1999 to today, it's still performing great. So 7 years was the lifetime of this one to do actual science, and it's still collecting data. It's amazing. It's more than 2 decades. So I worked on that a lot. Landsat is the US Geological Survey, another government organization in the US. They have a Landsat series in collaboration with NASA. And then Landsat 8 is around here, 2013 or so, I think. And Landsat 9 was just launched last week or so. It's right here on the left side of the picture.
So most of this data,
yeah.
Is it like free, or do we need to pay for this data?
It's all free. They have APIs. You can stream the data. You can download the data. And NASA is now moving to the cloud, where all this data will be available in Amazon S3 buckets. So if you have an instance up, EC2 instance, or an instance in Amazon AWS, then you can directly use the data without incurring any ingest or egress cost. Wow. And you can do all the analysis in the cloud. So that's happening right now. So a lot of data from these. Yeah.
So it's only your knowledge that is the limitation, because data you have, and purpose we have, like the purpose that you have already given, that there is a lot of crisis that's going to happen in a couple of years coming, in years coming. And if we are proactive enough to understand the data, to understand the,
Mhm.
to hypothesize the solutions and then test them, then it should be great, right? Yeah. So I
Exactly.
think
Yes.
I think this democratization of the entire data set opens up doors to everyone.
Mhm.
All right.
Yes.
Go.
So NASA is they have a mandate of like this moving the data to the cloud. Number one, number two, making the data open. They call it open science, open data. And third, making software that do the analysis and making it easier for the users to make sense out of the data, open source. So there is open science, open data, open source initiatives, and cloud initiatives going on at different sections of NASA and other organizations as well. Even though the talk is heavily focused on what we have at NASA, but the same is true for other space agencies and other organizations in and outside the US. Okay. So if you look here, I don't know if NISAR is here. Oh, NISAR is here towards the left of the image on um, right next to Landsat 9 is NISAR. NISAR is a collaboration between NASA and ISRO. So NISAR basically stands for NASA ISRO Synthetic Aperture Radar. It's a satellite that's going to be launched very soon. I think the launch date is early 2023, maybe January 2023. So maybe like a year and a few months left, like 14 months, 15 months from now. The NASA ISRO Synthetic Aperture Radar should be up and running. And actually, fun fact, NISAR is the satellite that kind of drove the entire NASA organization to go to the cloud, because the amount of data it's going to collect is going to be unprecedented. There are petabytes of data that it's going to beam down from space. And it will provide, for those who are familiar with the SAR imagery, it will provide it's a dual band system, and it will be the first radar imaging satellite to use dual frequencies. It will be used for remote sensing to observe and understand natural processes on Earth. And for example, there are two instruments on this, left facing and right facing. Radar always works like sideways looking. So the left facing instruments will study the Antarctica cryosphere, or the frozen ice. So the total cost is going to be like more than $1.5 billion, which is probably, NISAR is going to be probably the world's most expensive Earth imaging satellites ever when it's launched. And it's two big organizations, NASA and ISRO, collaborating on this one. It's very soon coming. So these are all the missions that are going to be there, studying solid Earth, water cycle, ecosystems, land, sea, continuum, how they connect. And so there's a committee called CEOS. Now we are coming to the part where, like, where can I get the data from? How can I download the data? So it's called CEOS, Committee on Earth Observing Satellites. It's made up of 61 different agencies from different countries. And together they operate more than like around 200 satellites, Earth observing satellites. So all the data from these 190 something satellites is free for use from all these different organizations. So you can see European Space Agency is down here, Canadian Space Agency, NASA is there, NOAA is the National Oceanic and Atmospheric Administration in the US, and a lot of other organizations. US Geological Survey is one. ISRO is in there, Indian Space Research Organization. So all these organizations, they dispense data, and you can go to ceos.org to learn more about this. It's they're working on making it available to the world for free to exchange technical information, and they are creating frameworks to increase the data usefulness and cost effectiveness. They're using the emerging technologies like cloud and AI and ML, all the future opportunities and all the current developments that are in the technical field. They are utilizing all of them, and they are raising awareness and having discussions with the user community on how to engage you. So they are out there looking for you. You just need to raise your hand or just go there, look for them, and then get all the data and a lot of resources. So these are all the different JAXA is here, Japan Aerospace Exploration Agency, JAXA. A lot of other, Korean Meteorological Administration is another one. So coming back to NASA. So NASA's Earth data is, Earth science data is called Earth data in NASA terminology. So if you ever hear Earth data, that means Earth science data. So NASA just calls it Earth data. So their website is called earthdata.nasa.gov. Their tools are called Earth Data Search, which is like a Google kind of thing for NASA Earth science data. So everything is Earth data. So be familiar with that word. They have a single sign-on called Earth Data Login. So you will need it. You can create free of cost. You just create that, and you, from all the data centers that distribute NASA data, you can use the same single sign-on login, which is Earth Data Login. So familiar with Earth Data Login. So NASA's Earth Observing System is called NASA EOS, Earth Observing System. The satellite constellation, the bunch of satellites that I showed you earlier, are all part of the NASA Earth Observing System. So the data acquired from those satellites is distributed by these 12 DACs. That's another term to be familiar with. DAC is a distributed active archive center, basically a data center. A data center that distributes NASA data, NASA Earth science data, or NASA Earth data is called a DAC. So if you hear that word, just be familiar with it. So there are different kind of DACs depending on what kind of data you need. For example, if you need SAR kind of data, synthetic aperture radar, like NISAR, when NISAR will be launched, it will go to ASF DAC on the top left here. ASF is Alaska Satellite Facility. It's at University of Alaska in Fairbanks in Alaska State. That's where they have data on sea ice and other things. So you can probably explore all these different DACs. So before coming to, so I worked for this one, ASDC in the bottom right here, the red box. It's the Atmospheric Science Data Center, DAC. So, and before that, I worked for the Oak Ridge National Lab DAC, ORNL DAC. And over there, they have the biogeochemical dynamics, ecological data, environmental processes, and things like that. So I moved from that to Atmospheric Science Data Center DAC. That was in Tennessee, Knoxville, or Oak Ridge. And from there, I moved to Virginia, which is where NASA's Langley Research Center is based. And within Langley Research Center, we have this data center called ASDC that deals with the atmospheric data center. We will talk more about my data center later on. There is LP DAC. For those of you who are interested in the land processes, LP stands for land processes. So if you want like land-based data of vegetation index, if you want to study the forests and the crops, Landsat and other things, you'll find the data there. And the other interesting one is PODAC on the left here. That's in California. It's at a NASA center called JPL. Most of you, some of you are familiar with the Jet Propulsion Lab. They create rockets, they create Mars rovers, and that's what they do. Their expertise is robotics on other planets and Mars and all those things. So PODAC stands for Physical Oceanography. If you need data related to ocean, if you want to study the oceans, so based on what you want to study, NSIDC, National Snow and Ice Data Center, that's in Colorado State. So all different ones, different DACs do different things. I am with the Atmospheric Science Data Center. Okay, next one. Just to give you an overview of my data center, you can go to all these different data centers, their websites, and look for the specific data. And I'll also show you where where to find the data from all the data centers without going to any of the data centers directly. So there is a single place called Earth Data Search, which is like Google of NASA data, and you can find data over there. But before that, let me introduce you to some of what we do at my center, which is Atmospheric Science Data Center. So we ingest, archive, and distribute. Ingest means we receive the data that comes down from the satellites after it is processed by the data provider, which is the science team that is kind of interpreting those satellite images that come down, beam down from the satellites. So what happens is the satellites only take pictures, then the science teams process that data to convert those pictures into usable products. The usable products could be sea surface temperature, or enhanced vegetation index, or NEVI or NDVI, normalized vegetation index. It could be surface reflectance. It could be leaf area index that gives you an idea about what fraction of the area is covered by leaves. It could be like any of those data products. So be familiar with that term also, data product. One satellite image can produce multiple data products. It can be just one set of images, but depending on which bands you used for processing, post-processing, you can get multiple products. For example, NDVI, which is the vegetation index commonly used, or EVI, enhanced vegetation index. It uses the red, green, blue, and the near infrared or infrared image channels to create the products. And then there are multiple other products, right? So ingest means we receive the data after it is processed. We grab the data from those producers and we store it. That means we archive the data, and then we distribute. We write services and tools to make that data available to the users, APIs, web apps, mobile apps, things like that. We also process and provide outreach and support to the research community. And ASTC is focused on 4 kinds of data: the radiation budget, what kind of radiations the Earth is emitting, the atmosphere is emitting; clouds, different kind of clouds, different types of clouds, what clouds do, and everything related to the cloud; aerosols, which is the suspended fine particles in the air. It could be chemicals, it could be methane, it could be monoxide, it could be ozone, anything else. That's part of tropospheric composition. The chemicals I was talking about, the methane and ozone, that's the composition of the troposphere. Aerosols is just the suspended particles, like dust and dust storms and pollutants and things like that. So currently, more than 50 different science projects, science missions, satellites that we process. So the primary ones, maybe some of you are familiar with those: Calypso, CATS, Ceres, Discover. DSCOVR is the satellite that's sitting 1 million miles away at the L1 point, which is the point of the balanced gravity between Earth and Sun. It's 1 million mile away, or 1.7 million kilometer, whatever. And looking at Earth, giving you images, that is DSCOVR. MISR is one of the instruments on the Terra satellite that was launched in 1999. Great instrument, you can do a lot of science with that. And then there is SAGE-3 instrument on ISS. ISS is International Space Station. So what they do is, some of the missions, what you can do is you can take the instrument, instead of putting it on a satellite, you can put it on the International Space Station, because it's already up there and going around Earth every 90 minutes. It makes one circle. So every 1.5 hours it completes the circle, and that's good enough. And some science teams, what they do is they are clever. They just make the instrument. Then again, it depends on the science question also. What kind of science question do you want to answer? The International Space Station is around like 500 something kilometers above Earth. Takes 90 minutes to go around Earth. You can put an instrument on the outside on the belly of International Space Station. There is a lot of wobble in there. You have to be mindful of that. But anyways, SAGE-3 is on ISS. There are multiple other instruments on International Space Station that beam the data down. A lot of other missions. There are future missions. We can talk about those. Maya is an interesting one. Maya is multi-angle imager for aerosols. It is going to study pollution in multiple areas, and one of the primary target area for this one is New Delhi and Kanpur area. So it's very interesting. And California, all the high pollutant areas, Beijing in China and Korea. A lot of those. So these are all the satellites that are upcoming. And Tempo is another cool one. It's again going to measure pollutants, but the Tempo one is not going to go around Earth. It's there are two kinds of satellites. One that go around the Earth and observe the entire globe. The other kind is called geostationary. So their orbital period is the same as Earth. So they just stay focused on one part of the globe. So they rotate with Earth. So the communication satellites are example of geostationary, because the communication satellites, that's why when you have a dish antenna for your TV channels at your home, your dish antenna doesn't move, because the satellite that it's communicating with does not move with respect to Earth. It's going around Earth. It's just looking at the same position. So those are geostationary. So Tempo is going to be geostationary. It's going to look down on North America, which is part of Mexico, Canada, all of America. And it's going to monitor the pollution and monitor forest fire at like a very high temporal resolution, which is multiple times in an hour. It's going to scan America from left to right, from right to left, or east to west, and then beam data at a very high resolution. You can do a lot of cool things when it's launched. I think the launch is maybe a year or two from now. Maya is pushed back. I am actively working on the Maya satellites. I'm very closely working with both Maya and Tempo, but Maya is more closer to what I work with.
Shall we take a couple of questions, Martin?
Sure.
I think there are a couple of questions. I think we can answer them very quickly. Question is, can we suggest, right, because we are already reached our time.
Oh, okay.
Okay. A question is, can we suggest some deep learning algorithm for mineral exploration? So my quick answer is that the algorithm model remain the same what you study in usual AI or deep learning courses, and the one that is being researched on, let's say, ImageNet dataset. It's essentially the similar model that will be used, and that's my understanding. Do you want to add anything, Martin?
No, I think that's good enough for this session. So I think I'm almost there. So worldview is not for downloading, but just to give you an exploratory view of all the data that is available. You can add different layers, and you can go to worldview.earthdata.nasa.gov. You can just look for worldview NASA, and you can add different satellites and look at this image. This was taken yesterday. It's the image from a satellite taken yesterday. You can move this timeline and then go through all the previous ones and zoom into your area of interest and see if you find something that is interesting to you. Next one is Earth data search, which is Google for Earth data, Earth science data from NASA. You can look by time, you can look by place, you can look by the name of the satellite, you can look by the phenomena that you are trying to investigate. So yeah, just look for Earth data search and you will find it. And I think we are coming to almost the last slide, deep learning applications. So there are two that I wanted to talk about. So I'll talk about the first one, the second one first, using natural language processing to assign correct labels.
Probably we can have another session on this. It'll be pretty useful.
Okay, sure.
Right. This has been like a very wonderful session. There are a couple of questions. Let's just address those and then, right.
Okay.
A question was, can you tell us something about new planet found in Whirlpool Galaxy? Okay. I have no clue. Over to you.
No, I have not read about it. I only read the news. I don't have any technical expertise on deep space exploration.
The question is, our Earth is surrounded by many number of satellites. Do satellites collide with each other?
Yes,
Okay,
look for Google for space debris,
okay,
space
okay.
DEBRIS. There's a lot of clutter out there, and with all these satellites, with Starlink, thousands of satellites from Starlink, and then Amazon is also planning to put more. There are
I
lots
see.
of private satellites, and this is going to be a problem in future, and they are working on how to address that. It's a issue that is becoming more relevant now.
Our question is, can we use Sentinel data for mineral exploration? And same, can we compare with Hyperion data?
Yes, yes, we can. But be aware that when you are using the Sentinel data, if we are using Sentinel-2, Sentinel-1, one of those is the SAR. I think Sentinel-2 is SAR, Sentinel-1 is in the visible spectrum. So with the visible spectrum, you can do, like, you can use other data like Hyperion and all. But for mineral exploration, I think it will be better if you use the SAR version of the data, synthetic aperture radar. That is Sentinel-2, if I'm not wrong.
A question from Kushan is that about the multiple satellites which are no longer functioning and orbiting the Earth, as in the space debris, can't satellite be auto-programmed to drift away from Earth to infinity?
Yeah, that's a good question. So all the satellites, they have some reserve fuel for bringing them down in a controlled fashion. So they are already bound by the gravity. They are always falling. So anytime you launch a satellite, from day one, it starts falling towards Earth. It's just that you have some fuel that keeps it in position, and when it goes like drifts away. But getting it out of the orbit would require more fuel because to escape the gravity and all those things. It's better to bring them down in a controlled fashion and then throw them in ocean, or they burn up. They burn up on re-entry. Yes.
Okay.
So, yeah, that's what it's done.
Okay. Okay.
Towards the end of their life.
All right. A question was, are they ABT ready? I don't know what is the context.
What's that?
Are they ABT ready?
Can you explain ABT?
I have no idea. I have no idea.
Please,
Let's
can
move
you?
on to the next question. Okay. A question from Varun is future job prospects in AI ML in earth science. Yes, just like okay, my quick view, just like computing got everywhere in every industry. Similarly, AI is everywhere where there's a computing, and earth sciences is definitely, you know, if there is a scientist, like for example, if you are an data, like if you are a scientist, research scientist working in geographical data or any domain for that matter, I would strongly recommend taking up AI machine learning course. And there is a lot of, it's expected out of any scientist or researcher to know about AI and machine learning. What do you say, Makan, about this?
Yeah, I think that's a good take on that one. I agree.
Okay. Another question is the process the process of for training the model with new stream of data coming from satellite consistently. So yes, so the process is same as the usual one, like the one, let's say you have an e-commerce company and there's a continuous data, as in when the new users are landing on your website and you have to take an action. So the process of handling the data, handling the entire software and hardware is kind of very similar. Even the machinery on machine learning and deep learning, it's kind of the same. Do you want to add anything, Makan?
I think that's a good answer.
Okay. All right. Okay. Right. Most of these are. A question from Aditya God is that how algorithms are used for capturing pages. How algorithms are used for capturing pages. As in pages of the data or pages of in memory? Was there any context for pages in your talk, Makhan? Images,
I don't
actually.
remember.
Yeah, yeah, it was actually images. Now here's the corrected one. So
Okay.
images, how algorithms are used for capturing images. Okay. So do you want to take this up, or like?
Yeah, I can try. For capturing, it's the hardware, the camera hardware that is on board. So those algorithms are built by or made by or programmed by the company that creates that. There are a lot of private companies that create images. Sorry, the imaging instruments, and those algorithms I am not very familiar with, but I think they are just depending on what spectrum you are capturing the image for, like red, green, blue, infrared, or far infrared, or ultraviolet region, or whatever you are doing multispectral. I think that will be very specific to the wavelength of the electromagnetic spectrum that you are trying to capture. So algorithms will be more from that domain of science, which I am not very familiar with.
Okay. Uh, there was a question. Can you please show the data from any data center? I think you can take a look at the URLs that he has shown. I think that'll be a good time. So that would be my quick answer. Makhan, do you want to add in that?
Yeah, sure. Just go to search.earthdata.nasa.gov, and you'll get to this page, and then you can just go here and type, let's say Miser is one of the instruments, or Terra. I used to work with MODIS images. If you say MODIS, and you can just click enter, and it will say like 1678 matching collections. You can say, oh, this is a vegetation index. You can just click that, and it will give you all the data available for vegetation index. And then you can just click on one, or like here, and then it will show you, okay, this is the data for this specific. Oh, that's in the middle of nowhere anyways. But yeah, so you can see all these granules highlighted, and you can explore this too.
Wonderful. Next question is from Nilesh. Will you elaborate in detail deep learning applications in earth sciences, please? Okay. Uh, you want to take up this one? I think we had
Yeah,
this.
I can just briefly tell you that I recently used, and Sleep, he's aware of this one. I discussed it with him in very like a lot of detail. The semantic segmentation using the deep learning convolution neural networks. I specifically use the UNet framework to do the semantic segmentation for identifying the land cover using Sentinel-1 data. And Sentinel-1 is the SAR one. It's the synthetic aperture radar data that I had to do this despeckle. So I'll take this opportunity to also tell you that the domain knowledge is the knowledge of the domain, or the science of that imagery of Sentinel-1 was much more important than knowledge of the semantic segmentation or using a UNet or any other framework. So keep your basics and domain knowledge strong, and then use the tools to answer that. So I use the despeckling of Sentinel-1 imagery for this specific mission. We can talk about this like in some other talk as well.
Yeah. A question is, how can we learn the relevance of different spectral images? How can we learn the relevance of different spectral images? Is it?
That's a very good question. So maybe buy a book on remote sensing, or there are a lot of online resources on remote sensing. So what they tell you is that different objects on Earth respond to different wavelengths of light or electromagnetic spectrum differently. And if you have that knowledge, okay, if you know that if you combine the infrared band with the blue band, the vegetation will pop out as like a prominent from the rest of the image. If you use a certain spectral band, then so water does not, like water is mostly black in most of the spectral bands. So if you acquire that knowledge, that will come from the domain knowledge, and that will come from if you know how different objects, plants, trees, how different species of trees reflect the reflectance characteristics of different objects. When you study those, you will gain a very in-depth knowledge of what band to use for what. But a lot of these has already been done for you. You can find just the water maps of the world created from these satellite imagery. So you don't have to do processing to figure out water. It's already done for you. It's called water mask for the globe. You'll get us. You don't have to figure out different species of trees from different spectral signatures. You can just download the land cover map that is generated by using Landsat or any other number of satellite images, and you will get a very detailed map of different kind of trees and crops and things from already existing algorithms that the science teams have developed and process the imagery for you. So it's ready for you to use.
All right. So I'll just walk you through. We have answered most of your questions. There are a couple of questions that we could not answer. Do come over to the discussion forum. You feel free to ask a question here. All right. And we would love to answer your questions over onto the discussion forum. And here what you see is, right, there is something called guided project. So go over to resources, click on guided project. You will get, and explore the projects. You will get fair number of projects that like hands-on projects, so that you get the process that Dr. Virdi was explaining about the machine learning and so on. You will get a fair bit of idea about it. All right. So feel free to visit the project section. These are free public projects that you can experiment. Similarly, you can take a lab like CloudX lab, and on a smaller data, you can do then experimentation. And in case you want to do some experimentation on little bigger data, like in couple of gigabytes, you ping us. If it's a public data, we'll put it as at a shared location, and you can do the processing. And so that's pretty much. Thank you, Dr. Virdi. It was so wonderful to have you here. It was actually very interesting to see. I mean, we had great audience, and the audience really loved it. So most of the people are really thankful to you for wonderful answers and great insights into the art sciences. And a bit more technical on the AI side, probably we'll plan again. And yes, it's so I mean, I'm really happy to see. I mean, I listened to every word of things that you said, and it was really helpful for me personally as well. All right.
Thank you. I think all the questions were very interesting, and I really enjoyed all the discussion and all the questions. I hope I wished I had more time to elaborate on those, but definitely we can take up in the discussion forums. But I totally enjoyed this. Thank you.
Thank you, everyone. Have a great day. Bye-bye.